Alright, so I already started these notes once and I got interrupted on a Google Meet and I wasn't sure if the camera was going to switch over, so I'm just going to pick up where I left off. So around October 27th should be these notes. We already did integration by parts day one, so the difference here to start off is we have definite integrals. Remember, a definite integral has limits of integration. So as we looked at this, we want to think of the lyate. And that says that probably you want to use u as a log first. So that's what I did here. And then the derivative of that is 1 over x. Over here, that left me with us with x to the negative 2. And here we want to integrate. So we're going to add 1 to the exponent. So that would have made it negative 1. And then divide by the new exponent. Okay? So that's where this came from. And then we do ultraviolet. U times V, so that gave us this. Now the thing about that is that that's the U times the V from the formula. We have U times V minus the integral of V to U, ultraviolet voodoo. Okay. So for a definite integral, this has already been integrated to get this part, so we're just going to put those limits on there like that. And then over here we would have minus, and then we have this. So that minus can come out there, and that's going to be from 1 to 2. And if we put these two together, that's going to be x to the negative 2 dx. Alright? So if we, instead of evaluating these separately, we can see that they're going to have the same numbers there. So I'm going to put it back together. So that would be over x. And then this would be plus, but then this, if we integrate, add 1 to the exponent, that'd be x to the negative 1, divide by the new exponent, that's going to become negative again. So that's going to be negative 1 over x, like so. And now we can put that together and evaluate that from 1 to 2. And in fact, since that has a common denominator, we can even put it back a little bit more, like so. So if we plug 2 in there, we're going to have negative natural log of 2 minus 1 over 2. And then we're going to have minus, and then that would be negative natural log of 1 minus 1 over 1. Okay, so if we want to, this is going to be 0. So I'm actually going to split this out. So this is going to be negative 1/2 natural log of 2 minus 1/2. And this is going to be a negative times negative. That's going to be a positive 1. Okay, so this is going to give us a positive 1/2. And then we might want to do a little symmetric property. Flip this over. Put that positive 1/2 first so we don't end up with an extra sign here. Minus 1/2 the natural log of 2. Okay? So, let's see here. So let's start off with a substitution here. So before we do integration by parts, we want to realize that this is a composite function. So that's going to be a little bit tricky. So I'm not going to use u right off the bat because I have the u as partial as integration by parts. So I'm going to let that be x. So x is going to be theta squared. So dx is going to be 2 theta d theta. Now, if I look over here, I have a theta squared, and then I can move this theta over here. So I'd have theta squared, and then theta d theta. So there's the theta d theta, and take half of both sides. So now, if we switch this up a little bit, the 1/2 is going to come out here. And theta squared is x, so that's going to be x. This is going to be cosine of x. And theta d theta, that's the 1/2 dx right here. So that looks good. Now I also do have to switch the limits of integration. So I need to plug this in for theta and find out these are all x values down here. So if I square that, actually that works out pretty nicely. That's just going to be pi over 2, and that's just going to be pi. Okay. Now we get to the u du and the dv and v. So how are we going to choose here? Well, one of the things you can do is you can try it one way and see what happens, and if it doesn't work out very well, then you can try it the other way. So if we take x as our u, the derivative of that would be dx. If we take cosine x as our dv and we integrate that, remember we're taking the derivative on this side, we're integrating on this side, so we integrate that, that's going to be sine x. And to test it, the derivative of sine x is cosine x. So that works out fine. So we're going to go this way. So that's our uv. So that's going to be x sine x. And that's going to be, technically we would have the, oh, don't forget the 1/2 up there. So this would be, actually let's just leave the 1/2 on the outside of the whole thing. And this was pi over 2 and pi. Alright, and then we have minus the integral, and then we have this part. So that's just sine x dx, like that. Okay? So, I guess I could finish off that bracket there. Now, leave that 1/2 out there, and we've got x sine x right here. Now, if we integrate this, the integral of sine is cosine, but it would be negative cosine because the derivative of cosine is negative sine. So it's negative, and then we have a negative times a negative, so that's going to be positive. So that's actually going to be plus cosine. So that's a little bit awkward, and that's from pi over 2 to pi. So if we plug those values in, we're going to have 1/2. And if we plug pi in here, we're going to have pi times the sine of pi. The sine of pi is 0, so that's going to be 0. And then we have the cosine of pi, that's -1. So we're going to have that. Now we want to be careful here to use parentheses because we're subtracting in case we have to distribute. So pi over 2, sine of pi over 2 is 1 times pi over 2. So that's going to be pi over 2. And then, oh, hold on a second. Yeah, we plug pi into both those, and now we're plugging pi over 2 into both these. So that's 0 here. Alright, so this is going to be -1/2, and this is going to be negative pi over 4. Now, it'd be a good idea for you to pause and try one of these by yourself. Okay, so I think we had something like this the other day already, so this shouldn't be that big of a deal. I don't know if that's getting a little bit too crowded for us right there. Separate these a little bit. Okay, so we've got our u du over here, and dv and v. So here, you probably could do it either way. I'm going to put sine here, so that's going to be sine x. Derivative of sine is cosine. And on this side then, all that's left is cosine. Now, that should be a dx there, cosine dx. And over here, I guess on all these I could have been putting dx's also. Doesn't really probably matter because we're integrating it, and we don't use that. We don't use that one anyway. We use these two and these two. But so if we integrate this, that would be sine, and you can test that by taking the derivative. So we're going to get sine squared, and that's going to be from pi over 2 to 2 pi, minus the integral of pi over 2 to 2 pi of this one, which is going to be sine x cosine x dx. Okay? So what you should recognize is, like the one we had the other day, this is the same as this. So if we add this to both sides, we would get 2 of those. Equals, do I want to simplify that yet? Maybe not. Sine squared x pi over 2 to 2 pi. Alright, so then we would take half of both sides, or half the whole thing. So that would give us that original integral, and that would give us half of this. So we've got half of, and now we can plug this in, so we're going to have the sine of 2 pi squared minus the sine of pi over 2 squared. So 2 pi is 0, so that's going to be 0. Sine of pi over 2 is 1. Squared is 1, so that's negative 1, and negative 1 times 1/2 is negative 1/2. Okay, so that shows us what to do with definite integrals and integration by parts. Okay, so now when we have to do a repeated integration by parts, we can make a table for the repetitions, because sometimes it repeats several times. So you can compare this to page 491, example 4 in the Larson book, in the blue book. Alright, so I have my little table here, and I'm going to start with u, and I'm going to put x squared. So usually on this tabular method we want to put a polynomial on as u, because that's going to break down. So then we're going to take the derivative, and that's going to be 2x. We're going to take the derivative, and that's going to be 2. And we're going to take the derivative, and that's going to be 0. So we keep breaking it down to get rid of it. Otherwise the table would go on forever. So we want that side to end. And then on this side, so we would put the sine of x, and then we would take the derivative of that. So that would be, oh wait, we're integrating, actually. We're integrating on this side. So I guess I could put my dx there. I could put my dx here and here. Okay. So now So on this side we're integrating. So if we integrate that, the derivative of cosine is negative sine. So this would have had to be negative for that to be okay. Now if we integrate that, the integral of that is going to be negative sine. Because the derivative of sine is cosine, but it's negative, so it needs to stay negative. And then stepping back from there, the integral of that would be cosine. Because we take the derivative of cosine, we get negative sine. So that's nice. So remember, we're integrating on this side. That's dv. That's u. And we're integrating on this side. And we're taking the derivative on the other side. Alright, so what we're going to do here, remember we go diagonally like this, and like this, and like this. And we need to follow this pattern where this is going to be positive, this is going to be negative, this is going to be positive. And that alternates. So it always starts positive and then it alternates back and forth. Okay? So if we go to do the first one there, that would be negative x squared cosine x. Alright? Now, then we go to the next one. So we're not going to put the integrals after there because we're doing multiple steps. So we could put an integral on this, but then we would end up doing this same process again like we did in our notes right before this, where then we did a UV integration by parts on the side. So instead of doing that every time, we're just going to keep going. So the next one, so there's our first diagonal. So our second diagonal would be right here. That's a negative times a negative. That's positive. So that's going to be plus 2x sine x. Now we come down here to this next one, and that's positive, and that's going to be plus 2 times cosine. Okay? And then the dx is, we're integrating those out, so that would be gone. Now this last one would be negative 0 times cosine. That would be 0. So that last integral where we subtract the integral, ultraviolet voodoo, and we would do voodoo, but that's 0, so that's going to be gone. Okay? But don't forget to put your plus c. So what we've done there is kind of bypassed the voodoo part. Remember, it's ultraviolet minus voodoo. Okay? But this part, we are taking care of that by keeping the table going, by doing it again and again. And then the last integral, which would be in between here, that's going to be 0 times that. So that last integral is going to be 0. Even if you don't understand why, I mean, you can memorize what to do. You should be able to. So, let's try that again, and keep in mind, what do we want to look at? We want this. We want the polynomial, because if we integrate that down, that's going to go down to 0, or a derivative, sorry. So, x squared minus 1, derivative is 2x, and derivative is 2, and derivative is 0. So kind of the same thing that we had over there. Now, this starts off as e to the x dx. If we integrate that, we get e to the x. And that's it, over and over again. Okay, so that was dv. This side was u. Alright, so now we're going to do that same thing. So there's that. Remember, this is plus, minus, and we're going to have this, then we're going to have this, and that last one again is going to be 0. It's going to knock that integral off at the end, which is nice. So notice how, a couple things here. This is a definite integral, and notice how all of these have e to the x in them. So I'm going to factor that e to the x out. Okay? So we had e to the x times x squared minus 1. I could put that in parentheses if you really wanted to, but it shouldn't really matter. And then here, we're going to have minus 2x. And then here, we're going to have plus 2. So I guess if I want, I could put that there. Just because I had the brackets, I figured I might as well use the parentheses. And then that's going from 0 to 1. So we can simplify in here a little bit. X squared minus 2x plus 1. So if we plug in 1, we're going to get e to the first. And then if we plug 1 in here, we're going to have 1 minus 2 plus 1. So that's going to be 2 minus 2, that's 0. That's a little awkward. Minus e, plug in 0, e to the 0. And if we plug in 0 here, that's going to be 0 minus 0 plus 1, which is just 1. So 0 times, that's 0. And that is just, that's 1. So that's negative 1. Alright, so there were 2 of those, 4 and 5, tabular, which leaves us with 1 left in today's notes, and that is going to be an arctangent or inverse tangent. So let's think about what we could do with that. See if you have any ideas. You could pause and think. Alright, so if we think about this inverse trig function, that Lie8, a mnemonic device, logarithms, there's no logarithms, but the I in Lie8 is for inverse trig. So that means that we want to use the inverse trig function here as our u. And if we're using that as our u, then the only thing left is for dv is to be dx, because that's all that's left there. Okay? So now if we if we take the derivative of this, the derivative of the inverse tangent, I don't know if you still have that memorized, probably I don't, but tangent, remember there's no square root and it's positive. So that's going to be 1 plus x squared dx. And if we integrate here, that's going to be x. Alright? So we're going to go this way. So u, remember ultraviolet, UV, ultraviolet, UV. So that's going to be x times the inverse tangent of x, and that's going to be from 0 to 1, minus the integral, and we're going to go this way, here. So that's going to be x over 1 plus x squared. I thought about switching that around, x squared plus 1, but it shouldn't really matter. Okay, so now we need to do something with this. We can also deal with this at the same time, or not at the same time, whatever. So if we plug in a 1 there, we would have 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0. Well, 0 times, that's going to be 0. Okay, now if we think about the inverse tangent of 1, what angle, the tangent of what angle gives us 1? That's pi over 4. So that is going to be pi over 4. Now, come back over here. This is just a normal u substitution integral. U substitution. So I'm going to let u, and you guys should be able to pause this, and oh, I'm going to use w instead, because we already used u up there. So I'm going to do w substitution instead of u substitution. I mean, you possibly could use u again, I just think it's a little bit dicey. So I'm going to let w be 1 plus x squared, so dw is going to be 2x dx. Now I have an x dx right there, but I don't have the 2, so I need to divide both sides by 2. Alright, so that would give us, so I'd have an integral here. I have the 1/2, which I should factor out in front. I should plug these in, so 0, that's going to be 1, and plug 1 in there, that's going to be 2. Okay, and then that's going to be 1 over w dw. Okay, so that's minus 1/2. If we integrate that, that's the natural log. The derivative of the natural log is 1 over. So the integral of that is the natural log, and that's from 1 to 2. So that's going to be pi over 4 minus 1/2 times the natural log of 2 minus the natural log of 1. The natural log of 1 is 0. E to what power equals 1? E to the 0 power equals 1. That's 0. So that's it. So that's pi over 4 minus 1/2 natural log of 2. All right. So it's about that time.